Drop a chunk of pure sodium metal into water, and it explodes. It is highly volatile, violently reactive, and incredibly dangerous to handle. Pure chlorine is an equally dangerous extreme. It is a heavy, toxic, and highly corrosive gas that destroys almost anything it touches. Yet, if you combine these two lethal elements, they neutralize each other to form sodium chloride, ordinary, life-sustaining table salt. This transformation is driven by a structural state present in almost every piece of matter in the universe: atomic instability. Looking at this model of an atom, we see the outermost ring, the valence shell. The Octet Rule requires exactly 8 electrons here to achieve thermodynamic peace. But excluding noble gases, atoms lack this perfect 8. They carry empty slots, making them inherently unstable. The physical world exists because these unstable atoms are constantly interacting with one another, searching for the electrons they need to reach balance. To see how atoms find that balance, we have to look at the specific structural deficits of our sodium and chlorine. Here is a sodium atom. Its outermost shell contains 1 isolated electron. Right next to it is chlorine, featuring 7 outer electrons and exactly 1 empty slot. Sodium achieves stability by ejecting its valence electron, which jumps and locks perfectly into chlorine's empty slot. Because electrons carry a negative charge, losing one makes the sodium atom positive. Gaining that electron makes the chlorine atom negative. These newly formed opposite charges create a massive electrostatic attraction, aggressively snapping the 2 distinct atoms together into a tight, inescapable lock. This intense electrostatic lock between a metal and a nonmetal is an ionic bond. This bond doesn't just link 2 atoms, it builds a massive repeating structural grid known as a crystal lattice. Ionic bonds trade individual chemical volatility for rigid structural strength. Total surrender works for sodium, but consider what happens when atoms interact and neither side is willing to give up an electron, like hydrogen and oxygen. This oxygen atom holds 6 outer electrons, requiring 2 more to fill its octet. 2 hydrogen atoms appear, possessing 1 tightly held electron each. Since neither yields, they compromise. The hydrogen orbits overlap with the oxygen, allowing electrons to circulate through all connected shells simultaneously. This overlapping shared electron structure is a covalent bond. The sharing isn't perfectly equal. The oxygen atom pulls harder on the shared electrons, causing a slight polarity within the unit. Unlike the infinite repeating grids of ionic bonds, covalent sharing creates discrete, independent packets of atoms. When total transfer is impossible, sharing electrons allows elements to lock into these self-contained, versatile chemical molecules. These microscopic solutions directly dictate the physical properties of the materials we interact with every day. The electrostatic grid of ionic bonds creates extreme hardness, but strike that grid, and the internal charges repel each other, shattering along strict geometric lines. The thermal energy required to break this grid apart is massive. It is the reason table salt will not melt in a standard kitchen frying pan. Covalent bonds, by contrast, forge independent molecules. Because these molecules aren't locked into an infinite grid, they are free to move past one another, allowing covalent structures to flow and flex, forming the liquid water we drink and the oxygen gas we breathe. These same flexible bonds are responsible for constructing the complex carbon chains of our own DNA. The entire physical reality around us, whether a rigid crystal or a flowing liquid, is the macro-scale result of unstable atoms sharing or transferring their electrons to find balance.